Okay, I started the recording. Okay, let's get started. So homework 7 is due today. Does anyone have any questions about either of the two problems in homework 7, 1 or 2?
Number 2.
So it's a fairly simple assignment. This one is just calculating probabilities that your random variable takes. 2e. Okay, great. Okay, so for 2e, this is the problem for 2e. It says something else in the chat. Someone else. Okay, so 2. Okay, so let x be a standard normal random variable. Find little z if the probability that x will take on a value. Find little z if the probability that x will take on a value between negative little z and little z is 0.8904. Okay, so let's go to Word. This is number 2 from that assignment. Okay, so and so the question is about part E. That's A, B, C, D, E. Okay, good. Okay. So the question's about part E. So 2E. Okay, so we want the probability that x will take on a value between negative z and c. So probably negative z is strictly less than capital X, strictly less than little z. Okay, so this is equal to x, the standard normal random variable. So since capital X is a standard normal random variable, we can use the table that we usually use for capital X. Okay, so so the probability that's in this interval is equal to the probability that capital X is less than little z minus the probability that capital X is strictly less than little negative little z. Okay, and adding an equal sign doesn't matter, so I can make this less than or equal to or less than, and it doesn't change anything. Actually, again, we'll keep it less than. Okay. Oh wait. Okay. So wait. Okay. Let me fix this. Okay. So okay. The table gives you values of the probability that 0 is less than x less than little z for values of little z. Okay. Right. Where capital X is a standard normal random variable. R dot B dot is short for random variable. Okay. So we just want to change this in terms of those probabilities. So this is equal to the probability that 0 is less than x less than little z plus the probability that negative little z is less than x less than 0. And this is equal to, by symmetry, this is the first probability is the same. But the second probability is equal to the probability that 0 is less than x less than little z. Right? So this probability, which I'm going to color in red, is this equal to this probability by symmetry. By symmetry. Okay, so I put the red there because that's corresponding to the reason the two red terms are the same or equal. Okay, so this is equal to now, this is equal to 2 times the probability that 0 is less than x less than little z. Okay. So we want to find the value of little z. If the probability that x will take on a value between negative z and z is 0.8904. So the value of this probability is 0.8904. Okay, so we found that this number 0.8904 is equal to 2 times this probability. So that tells us that the probability that solving algebraically, like this is a variable, is showing that this probability is equal to 0.8904 divided by 2. Right? And so you just divide that by 2 and you get 0.4452. Okay, does that make sense? Okay, so does that make sense? So the problems are basically similar. A through E are basically similar to E. If you know how to do E now, you can just take this method and apply it to the other parts. Does anyone have any other questions about this homework? Anyone?
Yeah, Professor.
Before we get
Actually,
started?
in number 1A.
Okay, so then we need to keep moving. So so now we go to this lesson. Okay. Okay, so at the end of last class, okay, so at last class, we talked about the normal distribution. So we found probabilities for normal random variables. And so we used the table to calculate probabilities of a standard normal random variable. Then we talked about how to relate the probability of just a normal random variable with the probability of a standard normal random variable, right? So we did this, we changed the interval. For starting with just a normal random variable, we translate this probability in terms of a standard normal random variable, right? Where z is equal to x minus mu over sigma, okay? So when x is only a normal random variable, you can define a new random variable z to be equal to x minus mu over sigma, and z becomes a standard normal random variable, right? Mu is the mean of x, and sigma is the standard deviation of x, okay? Okay, and so we calculate probabilities using that. We did an example. Okay, so that was very quickly last class. You can read that again if you need to. If you need to. Okay. Sorry. Okay, so. Okay, so that was the end of that section. So this lesson, we are starting with chapter 6. Okay, so chapter 6 is on mathematical expectation. Okay, and so 6.1, this chapter, is on the mathematical expectation of a random variable. Okay. So, okay, so basically to introduce this, the most important number associated to a random variable is the expected value. Okay, so the expected value is the most important number that you can associate a random variable with. Okay, so right now I'm just making lots of titles. So, so here we're talking about the expected value. So this is the notation for the expected value. Definition. Okay. The mathematical expectation of a discrete random variable, capital X, with probability function little f of x, is the quantity E of x, which is equal to the sum over x of x times f of x, where the sum is taken over all possible values, little x, of capital X. Okay, this is provided that this sum, still over all possible values of x, except where this is the absolute value of x here, provided that this sum, that this series converges. And so what that means, which means the original series converges absolutely. Okay, so when a series converges absolutely, you're saying that the absolute, instead of taking the sum of the terms, you take the sum of their absolute values. That's when a series converges absolutely. So what it's saying is that the expected value of a discrete random variable is equal to this sum, where the sum converges absolutely, where instead of taking the sum of the original values, you take the sum of the absolute values of these values, right? Because f of x is non-negative, its absolute value is the same as itself. But x could be negative, and so you write the absolute value of x here, but you're really thinking of the absolute value of x times f of x, which is the same as the absolute value of x times f of x. Okay, so this is the definition of the expected value of the random variable x. It's a sum over all possible values of x times f of x. Okay, note that e of x is also denoted by mu. Okay, so this is the Greek symbol named mu. Looks like that. Okay, so this symbol is often used to denote e of x, the mean or absolute value of random variable x. Okay, so in example 6.1, we see what this is. So let x be the numerical value, numerical outcome of one roll of a die. Find e of x. Okay, so the goal is to find the expected value of this discrete random variable x. It's a discrete random variable because there are only a finite number of possible outcomes in the experiment. There are only 6 possible outcomes of rolling a die: 1, 2, 3, 4, 5, or 6, right? So the possible values of capital X are 1, 2, 3, 4, 5, and 6. The probability function of capital X is f of x is equal to 1/6 for x equals to 1, 2, 3, 4, 5, 6. Okay, so that just means that right, the probability function is what tells you the probability that your random variable capital X is equal to some value little x. And so the probability that the roll is 1, 2, 3, 4, 5, or 6 are 1/6 for each. Okay, so if you want to find the expected value of this discrete random variable capital X, it's equal to, by definition, the sum over x of x times f of x, provided that this series converges absolutely. Okay, now, so what you do is you say, well, the possible values of x are 1, 2, 3, 4, 5, or 6. So you take each of them and you multiply them by the probability that x takes on that value. So it's 1 times f of 1 plus 2 times f of 2 plus 3 times f of 3 plus 4 times f of 4 plus 5 times f of 5 plus 6 times f of 6. Okay, so I'm just adding up these products. This is the first product. I'm using brackets not because they're needed, just to separate these products so you can see visually what's happening, right? I'm multiplying each of these things and I'm adding up products. Okay, each of these things in brackets are another term in the sum. Okay, so the sum is a sum of 6 terms, where each term is one of the terms I'm putting in brackets. So there's plus signs in between them because you're adding those 6 terms in the sum. Okay, so see that? Okay, so these are just values of x times f of x as x ranges from 1 through 6. Inclusive. Okay, but the probability that x takes on each value is just 1/6. F of x is equal to 1/6 for x equals 1, 2, 3, 4, 5, or 6. And so this sum of products is just the same as if you were to replace each of these with 1/6, because those are the values of f for each of those inputs. That's 1/6, that's 1/6, that's 1/6, this is 1/6, this is 1/6, and that's 1/6. So now you have the expected value by definition is equal to the sum of these products. And so you just multiply each of those things and you add them. So 1 times 1/6 is 1/6, plus 2 times 1/6, which is 2/6, plus 3/6, plus 4/6, plus 5/6, plus 6/6. Okay? So this is the same as 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. This is the same as the sum of the numbers from 1 through 6 is 6 times 7 divided by 2 by a formula. And so the sum of all the positive integers from 1 through 6 is 6 times 7 over 2. And so this is 21 over 6, or 21 over 6 is the same as 3.5. Okay? So note the formula I use is if you take the sum of the positive integers from 1 to n, it's equal to n times n plus 1 over 2. Okay? And so I just plugged in 6, n equals 6, and sum of the positive integers 1 through 6, 1 plus 2 plus 3 plus 4 plus 5 plus 6, is 6 times 7 over 2. Or that's 6 over 2, which is 3, 3 times 7 is 21, 21 over 6, or 3.5. The expected value is 3.5. So on average, what that says is that on average, if you were to keep rolling one die over and over again, eventually you would expect that the average would be very close to 3.5. That would be a result of, that would be something the expected value would tell you about this experiment. Okay, so example, that's by theorem. Example 6.2, a capital X be a discrete random variable with probability function f of x, which is equal to f of x, which is equal to 1/3 for x equals 3, and 2/3 for x equals 9. Okay, so there are only two possible values of capital X, 3 and 9. So it's a finite sample space, and so it's a discrete random variable. Okay, so the goal is to find the expected value of x. Okay, so we're just going to again use the formula. So E of x, the expected value of x, is equal to the sum of all possible values of x times f of x, where x, little x, the sum of all possible values of little x of capital X. This is equal to, well, 3 is one of the possible values, so 3 times f of 3 plus 9 times f of 9, because 3 and 9 are the only two possible values of x. Okay, right? Because the probability x equals 3 is 1/3, and the probability x equals 9 is 2/3. If you add these two probabilities, you get 1. There's no way that x could be another value of with some positive probability. So this is equal to 3 times the probability x equals 3 is 1/3, and then plus 9 times f of 9, and f of 9 is 2/3. So this is equal to 1 plus 6, which is 7. Okay, 9 times 2/3 is 6. 3 times 1/3 is 1. So 1 plus 6 is 7. The expected value of this discrete random variable is 7. Okay, so this is another definition. This is definition 6.2 in this section. This was definition, I'll label it 6.1. Okay, so the expected value definition is 6.1. It's a mathematical expectation of the discrete random variable x. Okay. Okay, so the second definition in this section 6.2 is the mathematical expectation of a continuous random variable capital X with probability density function. Little f of x is the quantity E of x, which is equal to the integral from negative infinity to infinity, x, f of x, dx, provided the integral exists. Okay. So e of x for a continuous random variable is this integral, provided that the integral exists. Another example, 6.3. Let capital X be a continuous random variable with probability density function f of x, which is equal to 81x squared for 0 less than x less than 1/3, and then 0 elsewhere. Find again the expected value of x. Okay, so we have this continuous random variable with this probability density function defined here. We want to find the expected value of x. Okay, so since x is a continuous random variable, we compute its expected value using definition 6.2 above. Okay, above we get the following. Okay, so we get that the expected value of x is equal to this, provided the integral exists. When you compute it and get the answer, if you get an answer and it's finite, that's proving the integral exists. Okay, so when we get the value of this and it's a finite value, we have shown that the original integral exists. And so we justify the first equal sign at the end when we get a finite number. Okay, so it's equal to this, and you have this function 81x squared for 0 less than x less 1/3 and 0 elsewhere. So this function f of x is 0 for any x value outside of that interval. And so that means that when you integrate this, you only have to integrate it from 0 to 1/3, because everywhere else, x times f of x is 0, because f of x is 0 everywhere else. And so between 0 and 1/3, you have x times f of x, and f of x is 81x squared there. And so the original integral from negative infinity to infinity is equal to the integral from 0 to 1/3 of x times 81x squared dx. And so this is equal to the integral from 0 to 1/3 of what you have x cubed, because x times x squared is x cubed, and then I'm going to move the 81 outside the integral by properties of integral, right? By properties of integral, we can move a constant inside or outside the integral. It doesn't change the value of the expression. Okay, so I moved the 81 out, and I now have definite from 0 to 1/3 of x cubed dx. So this is 81 times the value of that definite integral. Well, an antiderivative x cubed is x to the 4th over 4. And we're going to evaluate it from 0 to 1/3. And so this is now equal to 81 times, in brackets, the value of the expression when x is 1/3, which is 1/4 times 1/3 raised to the 4th power, and then minus that expression when x is 0. So that's 1/4 times 0 to the 4th. Okay. And so now you have that. And so then this is equal to 81 times, in brackets, you have 1/4 times 1/3 cubed to the 4th. That's 1/4 times, it's a little bit of a tongue twister, 1/3 to the 4th power is 1 over 81. 3 to the 4th power is 81. So it's 1 over 81 there, and it's minus 0. So this is equal to 81 times what's in the brackets, which is 1/4 times. Sometimes I put it times there just to help you see what I'm doing, times 1 over 81. So the 81s cancel, and you're left with this is equal to 1/4. So the expected value of x in this example is 1/4 by the definition 6.2, definition of the expected value of a continuous random variable. Okay, so now we have an example of computing expected value for a discrete random variable and one for a continuous random variable. And so the next section is why E of X is called mean of X, okay? And so this example illustrates why. So you have a class of capital N students. So a class of capital N students is given a test. The possible grades are A, B, C, D, and F with numerical values 4, 3, 2, 1, and 0 respectively. Suppose we choose a student at random from the class and let capital X be a numerical grade obtained by the student. What is E of X? What is the expected value of X in this situation, in this experiment? Okay, so you have a class of capital N many students, and then they're given a test. Possible grades are A, B, C, D, and F with numerical values 4, 3, 2, 1, and 0 respectively. Suppose we choose a student at random from the class and let capital X be the numerical grade obtained by the student. What is E of X? So first we introduce our own variable, and n sub x. Let n sub x equal to the number of students with grade x. Okay, so n sub x is the number of students with grade x. That means that f of x, which is equal to n sub x over capital N, for x equals 0, 1, 2, 3, 4, where f of little x, little f of little x is the probability that capital X equals little x. Okay? It's the probability. Remember, capital X is the numerical grade by the student you choose, right? So the probability that the numerical grade that student has is equal to some fixed value little x is f of x, which is n sub x over n. N sub x is the number of students with that grade divided by the total number of students in the class. Okay. So the notation is what makes this confusing, but the concept is very simple, right? You're just saying the probability a student has a particular grade is the number of students with that particular grade divided by the total number of students in the class. Okay, so notation is strange, but if you understand notation, this is a much easier way to talk about this mathematically than if we used something with more symbols, perhaps. Okay, so so E of X is equal to the sum over x of x times f of x, right? So this is a discrete random variable, right? So note capital X is a discrete random variable because there are only finitely many possible values of capital X, right? Those values are 4, 3, 2, 1, 0. Right? So you have a discrete random variable, and the expected value of a discrete random variable is represented by a sum like this. And so the goal is to find that sum. Right, so we're going to talk about what that sum is. So this is equal to, well, it's the sum over x of x times the probability f of little x, but it's equal to this fraction. So you can replace f of x with what it's equal to, n sub x over n. But now this is equal to, keep in mind that capital N is a constant. And so you can move this constant out. This 1 over capital N is a constant. So you can divide this entire sum by capital N instead. Instead of taking sums where you're multiplying each term by 1 over n, you could take the entire sum of the other two products and then divide the entire sum by capital N. Okay, so that expression is equal to the sum of the grades by students in the class divided by the total number of students in the class. Okay, so capital N is already the total number of students in the class by assumption. Okay, a class of n students means there are a total of capital N students. Now, saying that the numerator is the sum of the grades by students in the class, we just make this observation, right? For each possible value of x, for each possible grade, you're taking that grade and you're multiplying it by the number of students who received that grade. Okay, so you're taking each possible score and you're multiplying it by the number of students who got that score. That's the same as adding up the scores of all the students with the same fixed score. Okay, but you're doing that over all possible scores. You're just, instead of adding all the grades of all students in the class in any which order, you're in a sense arranging the students, you're separating them by the grades they got, and you're adding up one at a time all the students' grades, which each share the same grade. So you're adding up all the students who got a grade of 0, then you're adding to that the sum of all the grades of the students who got a 1, then you're adding to that the sum of all the grades of the students who got a 2, and then 3, then 4. You're then getting the sum of grades by students in the entire class. So the sum over x of x times n sub x is the sum of grades by students in the class. Okay, and so that means that you now have this e of x is equal to this fraction. But this fraction is the average grade in the class, right? If you add up all the grades that the students got in the class and you divide by the total number of students in the class, that's equal to the average grade. Okay? And so this shows that in this example that the expected value is the average grade. Okay. So it has to do with each example can be a little different, but in this example, the mean of capital X is interpreted as the average value weighted by their frequencies. Okay. Weighted by their frequencies because you're taking each possible score and you're multiplying it by the number of students who receive that score. The n sub x is the frequency of each of a grade little x. The number of times grade little x appears is n sub x, the number of students who got that grade. Okay, so the next example is example 6.6. Show if capital X is the number selected at random from a finite set, capital A, of numbers, then E of X is the mean of the set, capital A, of numbers. Okay, this is a little confusing to read. Show if capital X is the number selected at random from a finite set, capital A, of numbers, then E of X is the mean of the set A of numbers. Okay. So first, we suppose that our set capital A, we just give a way of representing. Capital A is a set, a finite set of numbers. So let's call capital A the set A1, comma A2, comma A3, comma dot dot dot, comma A sub n, such that A sub I is a number for all I between 1 and n. Okay, so each A sub I in this set is a number. It's one of the numbers in this finite set of numbers. And so we end this list at A sub n. So it goes from A sub 1 to A sub n. So there are n numbers in the set. Okay, but there can be more than one of the same number. So let's let f of A sub I equal to the probability that x is equal to that fixed value A sub I, where that's equal to k sub I divided by n for I equals 1, 2, up to including m, where k sub I is the number of elements in set A that are equal to A sub I. Okay, so k sub I is just the number of times the number A sub I appears in set A. Okay. Okay. Remember, there's in this set we've listed n elements, A1 to AN. So we have n numbers in this set A, but they can be repeated. Some of them can be repeated. So the total amount of numbers is little n. But for each number we choose, there could be different amounts, right? A sub I could appear 0 times, 1 time, 2 times. And so k sub I is the frequency of A sub I. K sub I is the number of times A sub I appears in set A for I from 1 to m. And we're stopping at m and not n because m is denoting the number of distinct elements in set capital A. Okay, so here lowercase m is the number of distinct elements in set A. Okay, so for each of the distinct elements in set A, we can find the number of times that distinct element appears in the set and divide it by the total number of elements in the set. That's the probability of that distinct element of that distinct element, and that distinct number in the set being chosen. Okay, so therefore, after all of that, therefore the expected value of x is equal to the sum, because we have a discrete random variable, it's equal to the sum from I equals 1 m of x sub I f of x sub I. So there are little m many distinct elements in set A, and so we want to add E of x is the sum of products, where each product is each distinct number in the set A, denoted x sub I, times the probability of selecting that number in the set f of x sub I. And so this is equal to, so you have this sum. Now, x sub I is what it is. Now f of x sub I, right? F of x sub I is given by this function here. So f of x sub I is going to be k sub I over n. Okay, and so then this is equal to, so in the numerator we have, sorry, just write it. Okay, so then in the numerator we have the sum from I equals 1 m of x sub I, right, sorry, that k sub I over n is f of x sub I. So I just okay, so then there we go. And so this is the sum of these products, where instead of dividing each term by n, you divide the sum by n, sum of products by n. So I'm just moving this 1 over n outside of the sum. And then 1 over n times the sum is taking the sum and dividing by n. So what does this say? Well, this says this is equal to, the denominator is n. The numerator is you're just taking each possible number in the set x sub I and multiplying it by its frequency, the number of times that number appears in the set. Taking the sum of products in this way is the same as just adding up all the numbers in the set. It's the same as a1, little a1, plus little a2, plus dot, 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 plus little a sub n, because there are a total of n things in the set. But the sum of the a's divided by n is equal to the mean of the set capital A of numbers. Okay, so E of x in this example is also the mean of something, in this case the mean of a set. So in both cases we see that the mean is the expected value of your random variable. Okay, so the next section is 6.1.4. It's the strong law of large numbers, and y, e of x, and y, e of x is called the mathematical expectation of capital X. Okay, so this is theorem 6.1. It's the strong law of large numbers. Okay. Let capital S be an experiment with sample space capital S. Let capital X be a random variable on capital S with its expected value x, e of x equal to mu. If S is repeated n times under identical conditions and x sub I is the random variable capital X on the ith performance of capital S, then the probability that the limit as n approaches infinity of the fraction x1 plus x2 plus dot 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 plus x sub n divided by n, the probability that the limit of that fraction is equal to mu is equal to 1. Or, in other words, we expect the average of many observed values of capital X to be approximately equal to e of x. Okay, so this is called the strong law of large numbers. I'm going to just move this down to the next page. This is all on one screen. Okay, there we go. Okay, so theorem 6.1, the strong law of large numbers. Let capital S be an experiment with sample space capital S. Let capital X be a random variable on S with its expected value equal to mu. If S is repeated n times under identical conditions, and x sub I is the random variable capital X on the ith performance of S, then the probability that the limit of the sum of the x values divided by n is equal to mu, the mean, the probability that the limit of that is equal to the mean is equal to 1. Okay? In other words, what this says is that we are almost certain that the average of the many observed values of x, which is this fraction, right? So the average of the many observed values of x, the average of the many observed values of x, which I'm going to label as blue, is this fraction right here. Okay, so the average of many observed values of x is adding up the values of those observed values, x1 plus x2 plus plus xn, and dividing it by n. That's the average of those observed values of x. Okay, so we expect, the we expect part is saying that the probability is 1. So saying that we expect is saying that the probability is equal to 1. So I don't know if the colors are distracting and make it hard to read or if it's helping you. I'm trying to associate these words with the equation. Okay, so I'm trying to explain what this equation is saying in words. So we expect, meaning the probability is 1. We expect the average value of many observed values of x, this fraction. So we're saying the probability, we are almost certain, meaning with probability 1, that this average, this fraction, the value of this fraction, is approximately equal to e of x. Okay, remember e of x is mu. So this to be approximately equal to. To be approximately equal to this part, which I'm going to put in green, that corresponds with the limit part of the expression. So the fact that the limit of this is mu is saying that when you take little n to be really large, sufficiently large, that the values of this fraction should be very, very close to mu. There's a much more rigorous way to explain limit, but you would need more sophisticated mathematics for that. But just, well, actually, calculus, you talk about that. But without going into without going to the difficult part of calculus, saying that the limit of this is mu is saying that when little n is really, really large, the values of this fraction are really, really close to mu. Okay, so with probability 1, when you take little n really, really large, the value of this fraction, the value of this average, is very close to mu, which is e of x. Okay, so that's what this is saying. Now I'm going to give this the color you can see, purple, and purple because mu is e of x. Okay, so that's directly equal to e of x. We expect, with meaning probability 1, that the value of this fraction, the average of many observed values of x, to be approximately equal to, in this case, the limit of this fraction is equal to e of x. Okay. Practically speaking, this sentence. We expect the average of many observed values of x to be approximately equal to e of x. Okay, so this is called the strong law of large numbers. So this is example 6.7. Suppose capital X is the length of life in years of a certain type of battery. Then f of x is equal to 3/4 times 2x minus x squared for 0 less than x less than 2 and 0 elsewhere. Okay, so suppose x is the length of life in years of a certain type of battery, then the probability density function is this. Okay, so for part A, show that the expected value of x, e of x, is equal to 1. Okay, so let's just calculate e of x. E of x is equal to, well, this is a continuous random variable. Okay, it's the length of life in years of a certain type of battery. Okay, so we're talking about time. And so when you're talking about time, you're probably thinking continuously. And so here we're thinking continuously. And so we're integrating from negative infinity to infinity of the PD of x times the PDF of x. dx. And so this is equal to, well, remember your PDF f of x is 0 outside of 0 to 2. Wait, okay, so it's this. It's f of x. Okay, that's the by definition. It's that. But now when you integrate, so you have x times f of x dx. But that's only for 0 to 2. Right, so you're integrating from 0 to 2 because f of x is only non-zero from 0 to 2. Right? If you integrate, if you consider everywhere else, the value is going to be 0. The integrand is 0 everywhere other than from 0 to 2. Still have to integrate from 0 to 2. So this is equal to, you take the constant out 3/4. You're still integrating. So you're integrating from 0 to 2. And now x times 2x minus x squared is 2x squared minus x cubed dx. Okay, this is equal to 3/4 times, well, this is 2/3 x cubed minus x to the 4th over 4. And you're evaluating it from 0 to 2. Okay, and so this is equal to 3/4 times. So now you just evaluate that when x is 2. You get 2/3 times 2 cubed, which is 8. minus, well, when you plug in 2 there, you get 2 to the 4th over 4. That's 16 over 4. Okay, so that's the value of the expression when x is 2, and when x is 0, you just get 0 minus 0. Right? This is equal to 3/4 times 2/3 times 8 is 16/3 minus 16/4 minus 0. So this is equal to 3/4 times, well, 16/3 minus 16/4 is then 5 1/3 minus, sometimes I use mixed fraction, 5 1/3 minus 4, just because in this case, mixed fractions it's easier to see. 5 1/4, 5 1/3 minus 4 is 1 1/3, which is 4/3. Okay, so 5 1/3 minus 4 is 1 1/3. That's 4/3. So 3/4 times 4/3 is 1. So E of x is equal to 1. Okay, so in part A, we show that E of x is equal to 1. Part B, if we bought 2,000 batteries, we can expect the average length of life to be 1 year by the strong law of large numbers. Okay, so this is more of an observation than a problem. Okay, so if we bought 2,000 batteries, meaning, so if we bought 2,000 batteries, we can expect the average length of life to be 1 year by the strong law of large numbers, right? X is the length of life of a certain type of battery. So the expected value is 1, right? So what that's saying is that for a sufficiently large number of repeated, if you keep doing the experiment a very large number of times, meaning if you think of a large number of batteries, then on average, that their length of life, their average length of life should be 1 year. Okay, that's what we said earlier about the strong law of large numbers and the probability of this limit equaling to 1. That we expect the average of many observed values of x to be approximately equal to E of x. We expect, meaning the probability is 1, that, we expect that the average length of life of batteries to be approximately E of x, which is 1 for a large number of batteries. Okay. Okay, so that's 6.1. That's the strong law of large numbers. It's very important. So 6.2 is applications. Okay, so in 6.2.1, we talk about fair games. So definition. A fair game is one in which the expected net gain of each player is 0. Meaning in the long run, you expect, and on average, every player should win a 0 amount. Okay, so that's the definition of a fair game. Okay, so so maybe an example of a fair game. Let's say you play a game where you roll a fair 6-sided die, and if you roll an even number, you get $1, and if you roll an odd number, you lose $1. Right? The expected net gain is 0. Right? The expected value, you can just intuitively see that if you roll an even number, you roll an even number half the time, you roll an odd number half the time. If you win $1 when you roll an even, and you lose $1 when you roll an odd, then over the long run, you expect that on average, you should gain $0, right? That's an example of a fair game. Okay? Getting $1 for rolling an even and losing $1 for rolling odd, that's an example of a fair game. It's fair to the player who's playing. Okay? right? It's fair because you're not going to possibly win. You're not probability wise, you're not expected to make money. You're also not expected to lose. It's fair for both you and the person giving you money. So example 6.8. In the game Shuck-a-Luck, a player pays $1 and chooses one of the numbers from 1 through 6. Okay, so a player pays $1 and chooses one of the numbers from 1 through 6. 3 dice are then rolled. And if the number he or she chooses appears 1, 2, or 3 times, the player receives 2, 3, or $4 respectively. Okay, so that means that a player pays $1 to play the game. He chooses a number from 1 through 6. Okay, and then he rolls 3 dice. So if the number he chooses appears once of those 3 dice rolls, he gets $2. If it appears twice, he gets $3, and if it appears 3 times, he gets $4. Okay, so the question is this a fair game? Also, if not, what should the fee be to make this a fair game? Okay, so if it's not a fair game, then what should the starting price for the player be so that it is a fair game? Instead of paying $1 to play, what is the new amount that would make the game fair? Okay, so what we should do is find the expected value of the game. Okay, so the goal is to determine whether or not this is a fair game by finding the expected value of the random variable in this experiment. Okay, so let capital X be the net gain of the player in units of $1, right? So when you're talking about net gain of a player, you're saying how much that player makes or loses, right? The net gain, net earnings or losses, but you need to tell the person in terms of what? Is it cents, dollars, right? And so forth. So we're saying in units of $1. So if the net gain is 2, then you're saying net gain is $2. If the fee is $1, the possible values of X are, remember, X is the net gain of the player. So if the fee is $1, the possible values of X are, well, you paid $1 and you make $0, then you would have lost the $1. It's -1. If you pay $1 to play, but you make $2, the net gain is 1. So then the possible value of X is 1. If you pay $1 and you make $2 and $3 in the game, your net gain is 2. And if you pay $1 to play and your net gain and you make $4, that's a net gain of 3. Remember that the player receives $2, $3, or $4 respectively if the number he or she chooses appears 1, 2, or 3 times. So if the number appears 1, 2, or 3 times, the player receives $2, $3, or $4. And if the number doesn't appear, the player doesn't get anything. So you either lose $1 because you don't get anything back after you pay $1 to play the game, or you make $2, $3, or $4 after paying $1 to play, which means you have a net gain of 1, 2, or 3. So the possible values of X, the net gain of the player in this game, are -1, 1, 2, 3. Okay, so we have 4 possible values of X. So now we want to find the probabilities that the value of each of those values of X, the probability that the net gain of the player is -1 or 2 or 1 or 2 or 3. And then we use the probabilities and the possible values of X to find the expected value. And if the expected value is 0, it's a fair game. And if the expected value is non-zero, it is not a fair game. Okay, so to find the probability function of capital X, consider each roll of a die a Bernoulli trial, and the appearance of the number chosen as a success in a Bernoulli trial. Then probability of success is 1/6. Because you choose a number, and every time you roll a die, you have a 1/6 chance of rolling that number. So then the probability of success is 1/6, and the probabilities of capital X are, well, the probability that X is equal to -1, right? The probability that the net gain is -1 is the probability that you never choose the number. You don't roll the number that you chose, right? So what you're saying is that you have 0 successes in 3 Bernoulli trials, where the probability of success is 1/6. Okay, so the probability that the net gain is -1 is the same as the probability that you roll 3 dice, and none of the 3 numbers you roll is the number you chose. Well, each of the 3 rolls is a Bernoulli trial, where the probability of success is 1/6, the probability that you rolled the number you chose, and the probability of failure is 5/6, the other 5 being numbers you didn't choose, right? So to find the probability that your number appears 0 times in 3 rolls is the same as having 0 successes in getting that number in 3 Bernoulli trials, 3 rolls, probability of success 1/6. So it's the value of B of 0.316. This is equal to, well, you can translate this, remember, so this has a value. It's now a function. You found the probability is equal to this function, and the value of this function is the answer of that probability. That you could write this out. This is 3 choose 0 times 1/6, the probability of success raised to the 0 power, times 5/6, the probability of failure cubed, because you succeed 0 times, fail 3 times. And so this is equal to 125 divided by 216. Right? It's just 5/6 cubed, because 1/6 is 0 power is 1. 3 choose 0 is 1. So 1 times 5/6 cubed is 5 cubed divided by 6 cubed. That's 125 over 216. So the probability the net gain is -1 is 125 over 216. So you're actually majority of the time, you don't roll your chosen number at all. None of the 3 dice is that number you chose. So the next possible value of x is x equals 1. You could have a net gain of 1. Okay, well, this is the probability that when you roll the 3 die, the number you chose appears exactly once. Because if it appears exactly once, you make $2 after paying $1 to play the game. So you pay $1 to play the game, you make $2, it's a net gain of 1. That happens when the number you chose appears exactly once. The number that you chose appearing is a success in a Bernoulli trial. There are 3 rolls, so there are 3 Bernoulli trials. And the probability of success in any Bernoulli trial is the probability that the number you chose is rolled, which is 1/6. This is a probability of 1 success in 3 Bernoulli trials, where the probability of success is 1/6. So it's the value of that function. And so it's this thing, except with the numbers changed. It's just 3 choose 1 times 1/6 to the first power times 5/6 squared. So that's the value of that function. And when you calculate that, you get 75 over 216. Okay, it's 3 times 1/6 times 5/6 squared. That's 3 times 1/6, which is 3/6. That's 1/2. It's 1/2 times 5/6 squared. That's 25 yeah, so it's 25 over 36. You could simplify this fraction. You would get 25 divided by 72. Okay, so 1/2 times 5/6 squared is 1/2 times 25 over 36. That's 25 over 72. Okay, so you could, that's in simplest form. So now the probability that x is equal to 2 is the probability that in 3 rolls of a dice, you get the number you chose twice. That means that you have 2 successes, 3 Bernoulli trials where the probability of success is 1/6. Okay, net gain of 2 is when the number you chose appears 3 times. It appears twice. Okay, because if it appears twice, you make $3. You paid $1 to play a game, so it's a net gain of 2. Okay, so then this is equal to now the value of this expression, except this is a 2, this is a 2, this is a 1. So 2 out of 3 times you succeed. So 3 choose 2, number of ways that you can arrange those 3 trials so that 2 of them are successes. It would be success, 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 failure, success, failure, success, failure, success, success. There's 3 ways. That's the value of 3 choose 2. So that's 3 times 1/6 squared times 5/6 of the first. And when you calculate that, this is equal to 15 divided by 216. Okay, when I wrote this down for me, I wrote 75 over 216 for the last one instead of 25 over 72, because then they all have the same denominator. So it's just easy to look at it that way. Okay, so next is the probability that x is equal to 3. This is the probability that you choose a number and you roll the die 3 times. You roll 3 dice, and all 3 of the dice are the number that you chose. This is very unlikely. This is the probability where you have 3 successes and 3 Bernoulli trials where the probability of success in each trial is 1/6. So now this is equal to 3 choose 3, which is 1, times 1/6 to the 3rd power times 5/6 to the 0th power. And when you calculate this, you get 1 over 216. There's a 1/216th chance that when you choose a number at random, when you choose a number, you roll 3 die, all 3 die are the number you chose. So it'll happen 1 out of every 216 times on average. Okay, so therefore, for a large number of dice rolls on the circle. Okay, so therefore, E of x is equal to, you take each possible value of x, multiply each of them by the probability that x takes on that value, and add up the products. So I'm just doing this, I'm just going to copy from the definition this expression so that I don't type it again. See, so we get E of x is equal to the sum over all possible values of x times f of x. So this is -1 times f of -1 plus 1 times f of 1 plus 2 times f of 2 plus 3 times f of 3. Okay, well, probably x equals -1. That's f of -1. So probably x equals 1. That's f of 1. Probably x equals 2. That's f of 2. Probably x equals 3 is f of 3. Okay, so those are the f's thing. And so we're just plugging in these numbers, these fractions, into these corresponding values of f. Okay, so this is equal to -1 times 125 divided by 216 plus 1 times f of 1, which is 25 over 72, or I'm going to write the other way. I'm going to write it 75 divided by 216, just because everything will have the denominator of 216, plus 2 times f of 2, which is 15 divided by 216, plus 3 times f of 3, which is 1 divided by 216. Okay, and so this is equal to, well, everything you could think of as a denominator 216. You have -125 plus 75 plus 30 plus 3. That's sum divided by 216. So that's equal to, the numerator is it's -17. Good. So -125 plus 75 is -50. -50 plus 30 is -20. Negative 20 plus 3 is negative 17. So the expected value is negative 17 over 216. As a decimal, this is equal to negative 0.0787. So the expected value is that, meaning that by the strong law of large numbers, the strong law of large numbers tells you that if you were to keep playing this game for a very, very large number of times, that you would expect that the average that you had made over the course of those many times you played this game, that on average you lost almost 8 cents, because this is negative 0.0787. So you would expect that the average after playing many games is that you would have lost a little under 8 cents on average per game. Okay? So the game is not a fair game, right? The expected value is not 0, right? So the game is not a fair game. That is because the expected value of capital X is not 0. On average, if a player plays the game many times, it is expected, what I just said, that he or she will lose about 8 cents per game. Okay, so for part A, well, the first question, is this a fair game? The answer is no, it is not a fair game. So the second question is, if it's not a fair game, meaning this is not one, what should the fee be to make this a fair game? So we asked the second question because it's not a fair game. What should the fee be to make this a fair game? Okay, so the next question is, what should the fee be to play this game to make it a fair game? Okay, so let little k denote the fee. Instead of the fee being 1, it's going to be k. Then, now let's compute the expected value with that assumption, the assumption that the fee is k. So E of x is equal to, well, if you were to make $0 because your number you chose never appeared, if you made $0 after paying a fee of k, the net would be 0 minus k, right? But the probability that you make a 0 is this probability, 125 over 216. 125 over 216 was the probability that when the fee was 1, that your net gain was negative 1. Or in other words, just that the number you chose appears 0 times. So now, even though the fee has changed, the probability that your number appears 0 times is still the same. It's still 125 over 216. Okay, so 0 minus k times 125 over 216 is losing the fee, which is k dollars, or negative k, because you've won 0 after paying a fee of k dollars, times the probability that happens, 125 over 216. Plus, well, you could make $2 after paying the fee of k dollars. And so if you made $2 after paying the fee of k dollars, then your net gain would be 2 minus k. The probability of having a net gain of 2 minus k is the probability that your number appeared exactly 1 time. And that's the probability we found earlier, that the net gain was 1. But now that the fee is different, the net gain doesn't have to be 1, but the probability of your number appearing exactly once is still 1. It's still 25 over 72, or 75 over 216, which I'm going to put 75 over 216, just so it looks easy to read. The next one is, well, if your number appears twice, you could make $3 and after paying a fee of k dollars. So if you make $3 by playing the game, after paying a fee of k dollars, that your net gain is 3 minus k. So the probability of having a net gain of 3 minus k is the probability that your number appeared twice to make $3 for playing the game. The probability that your number appeared twice is f of 2 in the previous part, when the fee was 1. That's 15 over 216. Okay, so, and then plus, well, you could also make $4 in the game after paying the fee of K dollars. So your net gain, if you make $4 after paying a fee of K dollars, is 4 minus K. And the probability of having a net gain of 4 minus K is the probability of the number you chose appeared all 3 times in the 3 dice rolls. That probability is 1 over 216. Okay, so now we have the expected value in terms of the arbitrary fee, little k. Okay, so this is the expected value in terms of the fee denoted by k instead of a fixed number. Okay. Now, in order for this to be a fair game with fee k, the value of e of x has to equal 0, right? So if we want to find the fee k that would make this a fair game, we want to find the value of k such that e of x is 0. So to find the fee k that would make this a fair game, we need to find the value of k that would result in e of x equaling to 0. To do that, we set e of x equal to 0 and solve for k in the above equation. Okay, so classes, just give me another minute or two, and then we can end class here. So we have e of x is that, and I set this equal to 0, and I solve for k. So I have 0 is equal to this expression. So 0 is equal to the value of this expression in terms of only one variable k. Okay, so solving this equation for k, we get that k is equal to 199 divided by 216. And that's approximately equal to 0.92. Okay, and so our conclusion is that to make this a fair game, you need the fee to be 92 cents to play. Okay, you need to make the game 8 cents cheaper in order to, instead of the average being that you lose a certain amount, it's then the average becomes even. It becomes a fair game because the expected value becomes 0. Okay, so the fee needs to be 92 cents per game to play. Okay, and so that's the end of that. Let me quickly see for a second if I want to assign homework for next class. Okay, so we are not covered yet enough for the next homework, and so there's no homework for next class. Okay, so class is done, and so I'll see all of you on Thursday. Okay, have a good night. See you all Thursday. Bye. So I haven't announced exam 2 yet because there's only 2 exams before the final, right? So the second exam and the final is near the end of the semester. Okay, so you don't have the second exam until after Thanksgiving break. Okay, so it won't be still for over 2 weeks. Okay, so there's more than 2 weeks away for the second exam. Okay, so it's more than 2 weeks away. Okay, so you're welcome. Okay, so have a good night. See you all on Thursday. Good night.
Thank you, Professor. Have a good night.